Good to see so many here. Yeah, as already said in the intro, I'm going to give you a dive into Flux, our model family for generating images and editing images. I was already, is this working? All right, let me look at this. Check. Oh yeah, this. Okay. Anyway, I'm Andy, co-founder of Black Forest Labs. And before I start with the model, I just want to give you an overview over what we're doing. At Black Forest Labs, we believe that visual media will become the central interface for human communication in the future. And we see us as the central infrastructure provider to power all the images and the videos that humans will use to interact with each other. And not only what cameras can capture, but even way beyond that. With that in mind, we started the company in August 2024. Since then, we've grown it to 45 employees, and we are distributed amongst two headquarters. The main headquarters is in Freiburg, in the Black Forest, actually, in Germany. And we also have an office here in SF. Cool. Since we released our image generation family, Flux, in August 2024, when we started the company, we've always structured releases in 3 different tiers. And we have constantly advanced the model family. And the tiers are as follows. We have the Pro models. They're super powerful and the fastest models that we offer. They are available via the BFL API only, and also via a couple of inference partners, like, for instance, Fal and Replicate, that I guess you also know them. And yeah, so they are super easy to integrate and scale to massive volumes nearly instantly. So this is the first tier. But as some of you might know, my co-founders and me, we've very strong roots in open source, similar to, I think, the founder, Guillermo of Vercel, who has invited us today. So we're also the original developers behind Stable Diffusion. And we still stick to that. We love the open source community, and that's why we also offer open weights and open source models. So we have the Flux Dev models. These are publicly available for downloading, for tinkering. They are fully customizable, and they offer a lot of flexibility for everyone who wants to use them. And finally, we have the Flux Schnell models. They are fully open source, and they are, in a way, the perfect entry point into the Flux ecosystem. All right, speaking of the ecosystem, if you look at the model atlas on Hugging Face, which visualizes the, I think, most used open source foundation models across domains, we can actually see that the single largest model on Hugging Face that has the largest ecosystem attached to it is our Flux Dev model. So that pretty much shows that I think Flux has already become the standard for open image generation. And obviously we are working to even advancing or extending our distribution in the future. So that much to the company. Let me see if it's still not working. Anyway, now to the main part of the talk. I wanted to dive into Flux with you, especially into our most recent model, Flux Context, which unifies text-to-image generation and editing. And I want to talk about today how to unify this. A couple of words before that, I think it's super important to have this joint model, because obviously image generation has a lot of nice applications, and we've seen this in the past year, but image editing has until really this year not kept up with the same speed in kinds of development. But image editing is actually a super important use case. It allows us to iterate over existing images and gives just people, I think, an additional level of control to actually, precisely modify images and stuff. This is super important. So with Flux Context, we've created, I think, the defining moment for image editing. It was released in June 2025. And it's a model that combines image generation with things for editing like character consistency, style reference, local editing, and all that at near real-time speed. We'll see this later. But as a good example, I brought you this image row here. From left to right, we start with an input image. Then we can prompt the model to remove this object from a face. And then we can set her into a completely new context while keeping the character consistent. This is super important, and there was a bunch of work done like in the past, fine-tuning to actually get this kind of character consistency into the model based on publicly available text-to-image models. But this instant image editing just allowed us to remove all that fine-tuning, which is always a bit effortful, I would say. And yeah, this is actually super amazing that this takes now 4 seconds or something. And yeah, finally, we can just change the scenery. In this case, in the rightmost image, we change it to a winter scene. Cool, here are a couple of more examples, what it also can do. So it's not only like good for character consistent edits or something, but it's also super nice for style transfer. We see that on the left side. So we take the style from the input image and map it to a new content, or we can do things like text editing, just changing here Montreal to Freiburg while keeping the font consistent. So it's just, and this is all combined in one model, and you can interact with it just via a super simple text interface. Cool. Very importantly, it's not only a general model, this model, but it's also very good at like solving specific important and interesting business problems. For instance, here in the left example, we can extract this skirt here from an in the wild image, and we get a product shot of this thing and a zoom in nearly instantly, again, a matter of seconds. This, before these editing models, took hours, days, or was not even possible. Similar to on the right side here, we can get from a sketch to a completely rendered output in a couple of seconds. Cool, so as I already mentioned, Flux Context combines text-to-image and image editing. We just saw a couple of examples. And let's briefly look what this actually means in terms of the model pipeline that you need to do. So here we see the classic text-to-image pipeline, pretty simple, we all know it. We use a text prompt, we push it through the model then does some magic. I'll explain to you how to create such a model in a second. And then we get out an image that hopefully, if the model is good, follows our input text prompt. Now, if you look at image editing, it looks quite a bit differently. We start with an image, which we show the model in a way, and then we don't add a text instruction that describes an entire scene, but only a change to that image. So here we have 2 conditionings. The first part we only have, or inputs. The first example, we only had 1 input. And now we describe a change, and the model should then modify the image according to the change. So some parts, as the church here, might should be the same after the generation, after the edit, others not. And this is what these editing models do. So it's quite a different task, and combining this into a single model is actually, I think, super nice because you can do everything. You can generate an image, then edit it afterwards, and yeah, get a lot of more flexibility in a way. I already mentioned that before we released these editing models, or before we saw these general editing models, there was a bunch of work done on fine-tuning text-to-image models to get this kind of level of control into the model, but this is now not needed anymore. We can just do this instantly, and this just brings down the time that you need to get nice results significantly. So this is it in terms of the pipeline. Now, let's look at how can we actually train these models. And there's a very important algorithm that I want to talk about. Oh, maybe this works again. No, still not. But I mean, I don't need it older. The algorithm that enables us to train these models is called latent flow matching, which is composed of 2 aspects, latent and flow matching. And I want to share a bit light on both of those. So let's start with the latent. This comes from latent generative modeling. This is an algorithm that me and my co-founders came up with nearly 5 years ago. And to explain what this means, let's first look at the following example. What I here visualize is basically 2 images, and for us, they look just the same. The left one is a JPEG, and the right one is the same image as a PNG. So the left one is an approximation of the right one, but we don't see any difference. Or is there anyone who sees a difference in these 2 images? I don't think so. Okay, now let's look at the file size of these images. The file size of the JPEG is actually close to an order of magnitude smaller than the file size of the PNG. This is quite remarkable, I would say, and we all know how image compression works, but just realizing that we can remove apparently a lot of information from an image without noticing it is quite remarkable, I would say. So apparently there's a lot of information in an image that we cannot perceive with our human eye. Another way to visualize this is to plot the perceptual similarity of an image, in the last example, the JPEG, and the approximation of this image, which is, in the last example, the PNG is the image, and the approximation is the JPEG of this image, and we can plot it against the file size. And when doing this, we get this plot. This is a conceptual plot, so this is not a like real, but it looks like conceptually like this. The perceptual similarity quickly increases and then stays at a constant level for nearly the entire file size. And this is what lossy compression algorithms like JPEG make actually use of. And you might ask now, okay, what does this have to do with generative modeling? It shows us that for a perceptual signal, or like a natural signal, like an image, for audio it is actually the same, to look real or to be perceived as real, we don't need to model all the high frequency details that we cannot perceive. And hence training a generative model in the pixel space on all these high frequency details would actually be a great waste of compute and time, because the model would learn to represent aspects that we don't even perceive, so it's pointless to learn those, right? And that is at the core of latent generative modeling. So instead of training a generative model in the pixel space directly on images, we learn a compression model that extracts a lower dimensional so-called latent space. And this latent space is what we see here in the center. Let's see if the laser pointer works. Oh, yes. So this guy. How do we learn this model? It's actually super simple. We use an image here on the left. We push it through an encoder. So effectively, this is an autoencoder. We push the image through the encoder. Then we arrive at this latent space. And the representation we then push through an operation that is called regularization. This forces the model to remove information from this latent representation. Can be implemented either discretely or continuously. And then again, we reconstruct the image from this latent representation. So classical autoencoder, which we train to basically yield similar reconstructions to the input. And very importantly, we add this discriminator loss. This can be imagined as a prior to make sure that actually only the details that perceptually matter to our human eye are reflected in this latent representation. And again, this regularization forces the model to reduce or to remove information. And the discriminator makes sure that it removes the right information that we cannot perceive. And like this, we arrive, once we have trained this model, at this latent space that then is used to train the generative model on. So latent space is a low-dimensional representation of the input image, or of an image that is perceptually equivalent. This is basically the latent aspect of the latent flow matching algorithm. Let's talk about the second, flow matching. And again, everything I explain right now happens in this latent space. So whatever we do right now, you see it here on the left side, every image gets embedded into that latent space, basically. So yeah, let's talk about flow matching. Flow matching algorithms are a general family of algorithms that are used to translate from a very simple distribution, which is, in our case, always the standard normal distribution. So we're now talking about probability distributions. I visualized it here. So this is a very simple distribution here. And flow matching algorithms translate this or provide us with means to train a vector field that is represented by a neural network, that guy here, to map between the simple distribution and very complicated distributions, such as the data distribution of natural images. So this is the data distribution. And what do we do to train this? The flow matching algorithm provides us with a very simple means to do this. All we have to do during the training is to draw a sample from this standard normal distribution here. So we have a sample, and then we assign it to one sample from the data distribution, a training example. And we couple this. And then we can construct this kind of vector that directly, linearly connects them. And if we do this for every example in our training data set, so just we take the example, we randomly sample a point from the standard normal, and we connect them, then we arrive at this kind of here constructed vector field. I could now talk a lot about the properties of vector fields. Vector fields, one important property is that paths cannot cross in vector fields. And we see that there's a lot of crossing going on. So this is obviously not the true vector field that translates between every point on this distribution or between this distribution and that one. The amazing thing about flow matching is if you just follow this rule, so we train the model to basically always predict these kind of vectors in between the data sample and the sample from the standard normal distribution, we arrive at the true vector field. And that looks then like this. So here we see that paths do not cross anymore. And the flow matching algorithm just guarantees this. This is a bit of a magic, but if we write it down mathematically, we actually see that this makes sense. And like this, we can actually then train the model to represent this true vector field that translates between the standard normal and our data distribution. And importantly, we want to be able to create images based on text inputs. So what we do is we condition this network always on a text input, basically, for every image example. Cool. So what are we doing when we're then sampling the model? We have this vector field that represents the mapping between those two distributions. What we do is then we start with a sample from the standard normal. We can sample from it with a computer, right? We all know that. And then we integrate along these trajectories represented by the neural network. We can do this with a simple Euler forward algorithm. Probably a lot of you might know them. So with a numerical integration scheme, we can just integrate along these trajectories here and then arrive at the data sample. We push it through the decoder again, and we arrive. So again, this happens in latent space, but here we arrive then in the pixel space again. And this is how I then can create images based on a text prompt. Cool. One thing, these numerical integration schemes are pretty, I think, they use a lot of steps. So they break this down, this process here step by step into up to 50 steps. So these latent flow matching models natively are pretty slow, and it takes about 30 seconds to 1 minute to generate an image, which is a bit long. I'll talk about how to make them fast very soon. But this is the general latent flow matching algorithm. So latent, again, connect or represents this latent space, or stands for this latent space where we train the model in. And the flow matching algorithm is what we just discussed here. Okay, now I explained how we create images based on text prompts, but how does this now apply to context, which is an editing model, right? This is also super simple. So this is a basic Flux context architecture. It's a transformer model. We all know that. It's a bit special, but the magic lies in the input. So we see here on the left side, the input into the model. First, we have the text input that just gets embedded by a text encoder into a set of text tokens. And then we have the image encoder we already saw in the last slides here, right? This guy here. This is what we now see here. So we have this image encoder, and there we have two sets of visual tokens. First, we have the set of the visual tokens that we actually use to generate. This is what will be the output image. And then we have, if we want to do image editing, a second set of visual tokens that just model or that just represent the context image. So the image, the reference image basically that I'm showing the model. And what we then do is we push this through this transformer model. It's a special one because It contains of so-called double stream blocks. These are, I would say, kind of expert models for each modality. So here we handle the visual tokens and the text tokens separately. For everything except for the attention operation then happens jointly over all tokens. And then we have standard blocks, standard transformer blocks, where we basically map all the input, the text tokens and the visual tokens with the same mappings before the attention operation. And like this, we can just go to image editing. What if we provide an input image here, and if we do text-to-image generation, we just don't provide this, and then we have only a text prompt as input, right? Cool. Last point here. How is the model so fast? So I don't know how many of you know Flux models. Maybe can you just raise your hand if you know Flux models? Oh, actually, yeah, a couple of. Okay, cool. So we all know that they're pretty fast, right? What do I mean when I say fast? We're basically most often orders of magnitudes faster than like comparable models. So here, for instance, if you look at obviously a very slow model here, but nice one, GPT image 1. Also here for editing, the Flux models are here more than 10 times faster, here even more than 20 times. So it's actually insane how fast they are compared to comparably powerful models. And the reason for that is an algorithm we developed 3 years ago. It's called adversarial diffusion distillation. And the goal of this algorithm is to bring down the number of numerical integration steps. I told you earlier, these are like most often 50 for a standard like flow matching model. And the goal here is to bring them down to as little as 4. Each numerical integration step means a forward pass through the neural network. So we can imagine that this just takes a long time. So we want to reduce it as much as possible. How does it work? We initialize 2 networks here, a teacher and a student. Both of them are initialized from the learned flow matching model via the algorithm I just showed you. And what we then do is to train the student to generate this, to get the same image quality in the output in 4 steps than the teacher does in 50 steps. This is the goal, and this is how we do it. We start with an image, we encode it again to latents here, and then we generate an output image for the student in 4 steps, or in the number of target steps that we want to do. And then we decode it again to pixels. In the beginning, this image here looks very blurry and very like just not realistic. And the goal is to improve this, obviously. So what we are doing is to use this again, encode it again to latents, and then do the same thing with the teacher, but in 50 steps, except instead of 4 steps. This then results in a high quality image, and we then use this distillation loss, basically just a loss to ensure that the distributions of the teacher or of the student matches that of the teacher. This alone would unfortunately not allow us to basically generate images that are looking real. So what we add is another discriminator loss. We saw this already for the autoencoder part in the latent generative modeling part of the talk earlier. This is basically the same. So we train a discriminator to tell generated images from the student from real images that we input here. And this happens in a Dino v2 feature space, or in a learned image representation model space in a way. And like this, we can actually then train the model to, in the end, generate realistic images. Instead of using 50 steps, it just uses 4 steps. And that's obviously a huge speed up. However, last point here, if we look at this thing here, it looks pretty, I would say, lots of overheads here, right? Because here we have to encode to latent. So we start in the image space, we encode to the latent space, then we decode again, then we have to encode again and decode again, and then this one is also encoding again into another representation space. A lot of overhead, a lot of memory costs related to this, and this is just very, it was when, after we came up with it, we were amazed by it, because allowed us to train fast models. It was so effortful to train this. So we thought about, okay, how can we actually simplify this? And the answer is always the answer. Just move it to the latent space whenever you handle pixels. So what we did is coming up with a latent adversarial diffusion distillation approach. It's basically very similar to what we did for the general latent generative modeling algorithm. We just move everything here to the latent space. Same thing, but instead of having to use these encoders and decoders, we can just get rid of those. And importantly, as a discriminator, we don't use Dino anymore, this image representation model. We use the teacher because that one anyway already lives in the latent space, provides us with a very nice image representation. So we can also use the teacher as a discriminator. And the rest of it is just basically nearly the same. We also remove the distillation loss. We found that we don't need it, which is also cool. So we have a loss less, and gets everything simplified. And like this, we can actually then, in a very memory efficient way also, bring down the number of integration steps from 5 to 4. So we have a 12.5 times speed up, and that's actually what we see as this order of magnitude in the plots I just showed you in the beginning of this section, right? So that's basically how we get a very fast model from a flow matching, from a base flow matching model. And now, before this talk ends, I actually have brought you a demo to show you Flux a bit in action. Let's see. So let's use it for image editing here. Let me check. Let me upload something. Have to. Oh, what are we doing here? Okay, let's. I think this one looks good. Yeah. Okay. Yeah. This is good. So here I start with a logo of my favorite football club, the SC Freiburg soccer club. I have to say soccer when I'm in the US. Okay, this is my favorite club, and I want to create a T-shirt with this logo. So let's say put this logo onto. Oh, this is okay. Yeah. Onto a T-shirt. Feels a bit weird because I don't have a screen in front of me. Okay, here we go. Generating. Let me make this a bit smaller, maybe like this. Okay, nice. We wait for a couple of seconds and we can get this nice logo on a T-shirt. And now the nice thing is we can actually go ahead, right? We can iterate on this. So let's say this logo is a bit too large, I would say. Make the logo smaller and put it on the rest part. Again, wait a couple of seconds. One, okay, cool. And we arrive at a result that is actually super nice. Did exactly what I wanted. So now the, oops, I want to start with this one again. And I want to now change the color because the color of the SC Freiburg is not black, it's red. So make the T-shirt, oops, red. Also super simple. Now we're at local editing. We're just editing like local parts of the image, right? In this case, the color. And importantly, we've now done a couple of edits and we see still that the logo is very consistently represented. So we can, this is the character, or in this case, object consistency that we saw. This is super important. Like think about a marketer who wants to like just has an object and wants to set it into a certain context, right? This is, in terms of the business value it creates, it's super important. And now finally we add a more complex transformation. We can say put the T-shirt onto a man walking in the park. Oops. So this is a complex transformation, and you could have said, okay, like things like changing the color you can do in Photoshop, right? Historically, but stuff like that is just not this is not what standard or earlier non-AI image generation tools used to be able or could do. And this is actually super nice. So here we have like now this kind of min, and finally, I think I'm at time, but let's do one last thing, which shows how general this model is. We can also do style transfer, right? So let's say make this a watercolor painting. All right, final one. And before, like these models, you would probably have trained a single fine tune for each of these kind of tasks, and now you can just combine it in one thing, which is pretty cool. Nice. So now I could print it out and hang it on my wall or something. Anyway, so yeah, I think this is showing the power of these models. Oh, that crashed something. I wanted to show you a last slide because I'm through, but we're hiring, and if you want to join us, please scan this here or visit the playground. The demo I just showed you, freely available. Thanks so much. I hope you learned something.